we have the mean value theorem for integrals. We already had a mean value theorem. Does anybody remember what the mean value theorem said?
If it goes to this point and this point, it has to cover all the points.
That's the intermediate value theorem. Good try, though. That's one of our value theorems. Okay, so if a function is continuous and differentiable, then what?
Oh, the slope of the between two endpoints, some point on there has to have the derivative.
Okay, so if the function is continuous and differentiable, then at some point on the interval, the slope of the secant line is going to equal the slope of a tangent line. Okay, and the point of tangency is going to be at some point in the interval. It's going to happen at least once. It's what's known as an existence theorem. It tells us that there is going to be a point where the slope of the tangent line at that point is going to be equal to the slope of the secant line. The secant line being the line that goes through the two endpoints, right? Okay, another way to think about it, the slope of the secant line is the average rate of change, and the slope of the tangent line is the instantaneous rate of change. So what it's saying is at some point, the instantaneous rate of change is equal to the average rate of change. And I used, for that theorem, I used the example of driving. If your average speed is 70 miles per hour from one point to another point, then that means that at some point, at least one time, your instantaneous speed also had to be 70 miles per hour. There's no way to have an average of 70 without having an instantaneous rate of change of 70 at some point. Okay, so the mean value theorem for integrals says that if f is continuous, it doesn't have to be differentiable, but just if it's continuous, then at some point in the interval, the function is going to take on this. Well, what is this right here? That's the average value. So at some point on the interval, the function is going to equal the average value. It's kind of the same thing as the mean value theorem, because if we go to the driving example, if we use this formula on the function that represents our speed to calculate that our average speed is 70 miles per hour, then we know at some point on the interval our instantaneous speed is going to be 70 miles per hour. So we did the mean value theorem with derivatives, and this is very closely tied to the derivative, but it's the mean value theorem for integrals. We will see a problem, at least one problem on the test with this. So there's two things I want you to do. I want you to find the average value of this function on this interval. Oh shoot, not that interval. Let me change it. Okay, sorry about that. We want to find the average value of this function on the interval from -2 to 2. And then we want to figure out at what point on the interval, or points, maybe more than one, does the function actually take on that average value. Can you evaluate this integral without a calculator? What does that look like? Let me ask you this. What does just this part right here look like? What is it, Evan? I thought you said something. Oh. What is it? It's the top half of a circle, isn't it? So this part right here is the top half of a circle. And so let me just graph that real quick. So the top half of that circle is going to be, well, it's going to go up to 2, it's going to start at -2, and it's going to go to +2. And it's going to look something like this. And remember, I'm leaving out this 2 here. This is just the underlined part. But if I take this area right here and I double it, what am I going to get the area of? The whole circle, right? So if I double this function, what I'm really doing is I'm getting the area of the entire circle, because I'm going to end up with the bottom half of the circle also. So that integral right there is going to give us the area of the entire circle. That circle has a radius of what? 2. Okay, so the average value is going to be what? Let's compute that. The average of f is going to be 1 over 2 minus negative 2. I'm writing this all out so you can see where it all comes from. Times the integral from negative 2 to 2 of this. So that's going to equal 1 over 4. And we said that this is just the area of the circle here, which is what? The area of that circle is 4 pi. So the average value of this function on the interval from negative 2 to 2 is pi. That's fun. Okay, that's the first part. Second part says find the value or values on the interval where the function takes on the average value. This is the mean value theorem for integrals, this part right here. Okay, so first of all, this is continuous on the interval from negative 2 to 2, which tells us that at some point, this function here is going to equal pi. In fact, this is going to happen at 2 points, as you could probably guess. So what we're doing here is we're looking for c values. So we're going to say that 2 times the square root of 4 minus c squared is equal to pi, and we want to solve that for c. I'll let you do that real quick. So I got c is going to end up equaling positive or negative square root of 4 minus pi squared over 4, which is approximately equal to what? What'd you guys get? We should be getting answers here that are between negative 2 and 2, because this theorem says that it's going to take on those values between there. You guys agree with Lauren? So, as I suggested, we're actually going to take on that value twice. This right here is not actually what this function looks like. It's just a representation of the area under this function. It's actually going to be the top half of an ellipse. And so if I draw that real quick, so the function looks something like this. We figured out that the average value is pi. So the average value of this function is going to be right around here. And it takes on that average value at negative 1.238 and at positive 1.238. Does that make sense? Just to kind of go back to the average value idea, what this blue line here tells me is that the area underneath the blue line between 2 and negative 2 is the same as the area underneath the curve between negative 2 and 2. So we have, what we're doing is we're changing an irregular area that's bounded by a curve into an area that's bounded by a rectangle, and rectangles are a lot easier to work with. Yes?
No, it's not 100% accurate, is it?